Hi, everyone. Welcome to the Power Hungry Podcast. I'm Robert Bryce. On this podcast, we talk about energy, power, innovation, and politics. And I'm pleased to welcome Matt Wald. He is a friend of mine. He is an independent writer and consultant and an expert on all things nuclear energy. Matt, welcome to the Power Hungry Podcast.
Thank you, Robert. Very glad to be here.
Now, I did warn you, I don't warn all my guests, but I warned you that our guests on this podcast introduce themselves. So imagine you've arrived somewhere, you don't know anyone, you have 60 seconds to tell them who you are. Please tell them who you are.
I am a person who has a very broad acquaintance with technology and energy and environment. What I do for a living is try to translate what the engineers are saying into understandable English. I do some writing for the Breakthrough Institute, for the American Nuclear Society. I covered energy and technology for the New York Times for many years. And I also worked for a few years at the Nuclear Energy Institute, the trade association of the nuclear utilities.
And you live in Washington, D.C.
I live a stone's throw from Washington, D.C. And actually, electrically speaking, I have just discovered that this building is connected to Washington, D.C. And if we put solar on the roof, it turns out we will collect credits from the District of Columbia, not from the state of Maryland, where we're actually located. DC is across the street. And in theory, we will rake in money hand over fist, but in practice, I don't think it'll work. But I'll get into that if you'd like.
Okay. And I asked you before we started recording, 38 years of the New York Times.
That's correct. Yes, I started prenatally.
So I wanted to have you on the podcast, and glad that we finally made this happen. You've written two very good pieces for the American Nuclear Society on nuclear fuel. Which is an issue, as you know, I am as well, adamantly pro-nuclear. But I also see in a very sober way what the challenges are for nuclear in the United States and more broadly around the world. The first piece was titled "On the Verge of a Crisis: The Nuclear Fuel Gordian Knot." So I want to talk about this, and I'm going to ask that piece, and I'll ask the question very directly: will the lack of nuclear fuel, and you described this looming shortfall due in part to Russia's invasion of Ukraine, will this lack of nuclear fuel choke the nuclear renaissance before it gets started?
It has certainly delayed it because many of the new reactors, the advanced reactors, not all but many, run on a form of fuel that is not commercially available except from the Russians. It is called HALEU. It is high-assay, low-enriched uranium, and let me explain that. In nature, a very small portion of the uranium is the isotope U-235, the stuff that splits easily. It's less than 1%. In the reactors we run today, we raise that, we sort out the isotopes and raise that to about 5%. The upper limit of low-enriched fuel, where you don't worry about proliferation, is 20%. Some of the new reactors are designed to run on low-enriched fuel, but it's just below that 20% threshold, 19.75%. And there's no place to get it at this moment. It's not a technical problem, but it is a commercial problem, and especially a problem of commercial inertia. If you were counting on Russia to supply it, you didn't build your own infrastructure to get it, and then you've decided it really isn't practical to import from the Russians anymore, then at least in the short term, you can't get fuel for these new reactors. An additional problem is fuel for existing reactors enriched to 5%, where the Western world is not self-sufficient. It's reliant on the Russians.
Well, this is so interesting because I remember a few years ago, someone came to me with, these reports about what was going on with Russian fuel and should we be worried about imports? And I was, I kind of had a very blithe attitude. Oh, well, no problem. They're the lower cost supplier, so we don't need to worry about this. But in reading your two pieces, and I'll have the links to those articles from the American Nuclear Society in the show notes, I mean, you make it clear that the U.S. kind of sleepwalked into this. And yeah. I'll read the key part here. You find let me see, here it is. You explained in 1993, The U.S., I'm quoting, throwing a lifeline to the fledgling Russian democracy headed by Boris Yeltsin, signed an agreement to buy high enriched uranium that had been intended for Soviet bombs. The uranium was downblended to below 20%, the legal dividing line between HEU and LEU, high enriched and low enriched uranium, and shipped to USEC, U.S. Enrichment Corporation, which downblended it further to the level commonly used in reactors, 5%. Over the next 2 decades, this enrichment met half the needs of the U.S. nuclear energy industry. So is that deal, which was megatons to megawatts, right? That was the kind of the branding for it.
Yes.
That deal coming back to bite us?
Partly, yes, it's contributed to the situation that's coming back to bite us. Certainly, if you're in the enrichment business, the last thing you want is for the market to be swamped by a government that's diluting its old weapons stuff. Certainly, the world is a better place because there's less high enriched uranium floating around, but there's a silver lining. There's less high enriched uranium. The cloud around it is we've let our enrichment capability wither, partly because of that deal.
Well, it is, so I'm going to push back on that. She said we've let our enrichment capability wither. It's gone, isn't it? I mean, we don't have any left, do we? Or I mean, walk us through that, because we're not producing any uranium oxide. You pointed to the EIA's data on that. I mean, we're now, the U.S. nuclear sector is wholly dependent on imports. Am I correct?
We got several different components here. One is uranium ore, uranium oxide, and there's lots of that available from places like Canada and Australia, although the low-cost supplier is Kazakhstan, which could also be a problem. Kazakhstan, when it was part of the Soviet Union, would ship the stuff for export through Leningrad. It has recently pioneered shipping it through Pakistan instead, all well and good, but Kazakhstan, it's a low-cost supplier. Whether it is a long-term reliable supplier remains to be seen. Just how much do you want to rely on a post-Soviet republic? After you get the yellow cake, the uranium ore from a mill at the mine, and you bring it to a factory, you convert it to a different chemical form so you can enrich it. You convert it to something called uranium hexafluoride. Essentially, you're mixing fluorine gas, and you end up with it in a form that can be sort of a gel or gaseous, and that's what you put into a centrifuge. I should add, by the way, fluorine is the basis of World War I nerve gas.
Right.
It's pretty toxic. The uranium is not, but the fluorine is. Our ability to do that conversion has withered away because the Russians do a lot of the conversion. Then you enrich it. The United States doesn't have any native enrichment capability anymore. We had something called gaseous diffusion, which was invented to build the first atomic bomb during the Manhattan Project in World War II. Those became obsolete. We did not replace it with anything else. There's one centrifuge plant running in the United States. It's in New Mexico, runs very well, but it's not sufficient to meet our needs. And because it is not an American technology, by international law, it can only be used for civil purposes. If we ever need enrichment for non-civil purposes, submarine propulsion, propulsion of aircraft carriers or weapons, we don't have a way to make it at this time, although we do have a stockpile. But the whole world relies on enrichment. I should say Soviet enrichment. It's enrichment left over from the Soviet era in the hands of the neo-Soviet government in Moscow.
Well, in that Russian supply chain now, I was looking at Centrist Energy, which is the company that is now the only company in the U.S. that has the ability to make HALEU, or only one that has that license, rather. They're not making it. They've proven, a demonstration project. But we're now 28% of all the nuclear fuel in American reactors is coming from the Soviets. Is that right?
From the Russians.
I'm sorry, the Russians. Forgive me. You mentioned
that's about right. But
old habits die hard.
That's right. They die hard in Moscow too. In a sense, it doesn't matter what fraction we get. We're in a global market.
Mm,
It's kind of like oil, where at the moment we're pretty much self-sufficient in oil. If there's a real oil shock in the Middle East, prices here will rise too.
sure.
Prices availability of an international commodity, it doesn't matter which particular supplier is yours. And Europe and Japan are also relying on a world market that is in which there's very heavy involvement from the Russians.
Well, but I'll tell you. I mean, reading your two pieces in the American Nuclear Society, and again, my guest is Matthew Wald, Matt L. Wald on Twitter. That's at Matt L. Wald on Twitter. It paints a pretty dire picture. I mean, I don't mean to be alarmist, but I talked about this on the podcast before. I went to Japan earlier this year, and I was there in February and March, and I went to the JNFL, Japan Nuclear Fuel Limited. They're building their own reprocessing plants. They're building their own enrichment capability. There's strong government involvement. The nuclear utilities in Japan are all in. They're all very cooperating very well. And I see nothing like that here in the United States. And so it seems to me that we've seen, and well, I'll ask the question this way. There's been a lot of investment, obviously, in the nuclear sector, billions into different reactor companies. So we've seen NuScale's gone public. There's a lot of money floating around. Has there been too much
Private money and your tax dollars, by the way, both.
Yes, and $1 billion or more in federal grants to the different industry, different companies. Has there been too much investment in the reactors themselves, or I'd use the oil and gas industries terms, in the downstream, and not enough investment in the upstream?
Yes, but it's a complicated problem. The problem is not that the Russians are going to cut us off, or that we're going to cut the Russians off. The problem is that the Russians might cut us off, or we might cut the Russians off. I don't know where your 401k is invested, but let me pitch you on an investment. We're worried about the Russians. How about if we spend multi-billion dollars in multi-years to build new enrichment capability, make HALEU, make the low-enriched stuff we use now, our bread and butter. Here's the catch. It won't be done for 3, 4, 5 years. In 3 or 4 or 5 years, who's going to be president of Russia? Will there be a war going on in Ukraine? What will the price of a unit of enrichment be on the world market? And the answer is nobody knows. This is not the kind of atmosphere in which corporate America, or you with your 401k, wants to sink money. It's just too uncertain. And the only party that can realistically do this is somebody with very deep pockets, which is Uncle Sam, at least until June 1st when we default on our debt. But you understand what I mean.
Well, so I want to come back to the government role here, because that's how you ended the second installment of your deep dive into the fuel supply issue for American Nuclear Society. But I'm glad you made that point, because I was looking at Centrist Energy and their website and their what they were, their recent press releases. It was earlier this year. So Centrist, again, is the only domestic producer licensed to produce HALEU. And then in February, they said a full-scale HALEU cascades consisting of 120 individual centrifuge machines with combined capacity of approximately 6,000 kilograms of HALEU per year, which they use that acronym, 6 MTU per year, could be brought online within about 42 months of securing the funding to do so. So I'm bringing that up because here is the company that is the only one that is licensed to produce HALEU, but they're saying, okay, well, we get the money. It's going to take us 4 years to bring this capacity on.
Well, and the 6,000 MTU isn't going to get you very far. Excuse me, 6,000 kilos isn't going to get you very far. Yeah.
Right. And you beat me to the punch there, because even the NEI's own data from their 2020 report expects the HALEU market will be 37 MTUs by 2025 and 130 by 2030. So, what Centrist could produce at 6 MTUs, that's a drop in the bucket compared to what this expected demand is. So I'm reading that because I'm trying to reinforcing rather what you just said about, well, how do you bet on this market? How does anyone bet on this? And that it would have to be the U.S. government to step in to have a major industrial policy, a national champion to make this fuel supply secure. But is that even a remote possibility at this point?
Well, in a way, we did it for oil. We built the Strategic Petroleum Reserve, and it was always measured in the number of days of imports that it could replace. We do have a very small, low-enriched uranium stockpile. It's good for 5 or 6 core loads. A core load is 1/3 of a core. If you've got 92 reactors operating and each is refueling in every 18 months or 2 years, 6 spares is not a whole lot.
6 spares for one reactor is what yours is. What is it?
Well, for whatever number of reactors you spread them among. Yes, right.
Okay, so but I want to make sure I'm understanding. So we do have, because you mentioned that in your ANS pieces,
right?
So we do have a reserve, but that reserve is only good for how long? If we spread it among all the reactors in the U.S.
A few minutes.
A few minutes. Okay.
Well, no, it'll handle 6 refuelings, but we do 40 or 50 refuelings a year.
Okay. Right, got it. Okay, 6 refuelings of 6 reactors, and we have 90, right? So
yeah, 92. Yeah, right.
92.
Right.
So this, what so would it be fair to say then that I'm jumping ahead here a little bit, that you believe maybe we need a uranium equivalent of the SPR, then a nuclear fuel equivalent funded by the federal government that would be the nuclear energy sector's equivalent of the SPR?
That would certainly be one approach, and bear in mind that what reactors produce is electricity, which is fundamental to the economy.
Right.
Oil has become somewhat less important over the years since this Strategic Petroleum Reserve was established. Electricity gradually becomes more important. We got a lot of money invested in machines that turn uranium into electricity, and uranium is what they run on. We're going to look pretty silly if we can't run those machines because we don't have low enriched fuel. So yes, one approach would be for the government to set a price at which it'll buy the stuff, and it'll guarantee a market at a floor price.
Right.
So that an investor would then say, well, if Russia straightens up and is allowed back into the world market and turns loose with all of its capacity and drives down the price of enrichment, at least I know I can still sell to Uncle Sam at a price that will cover my costs.
So it would be similar to contract for difference, I guess, using a different term, a contract term that would be reserved for domestic producers of the fuel, that so they could make sure they can compete in the international market
or survive.
Or survive, right?
You're in bed with elephants, essentially.
Well, so but you mentioned, so we're just focusing on the U.S., but I've thought about your piece and vis-a-vis the rest of the world. So it's this nuclear resurgence isn't just happening here. We saw, in fact, there was a headline today. Poland just announced that they approved the new Westinghouse design, the AP300, which is interesting because the design was apparently just unveiled. So I mean, it's miraculous how quickly that happened.
Yes, and they would like an AP1000 also. They'd like a whole bunch of things. In addition to that, Robert, as you know better than I do, we need a reactor we can sell to Nigeria.
Right.
We need, the whole world is electrifying, and we need them to do something other than coal.
Right.
So we've got a renaissance going on in Eastern Europe, especially.
Right.
Probably some growth coming in France and Great Britain. Japan is going to start back up. China is its own self-contained world for fuel and reactors. But we need reactors in South America, in Africa, other parts of Asia. And we need to persuade countries that would buy these things that the fuel to run them will be available.
Right. We not only need the technology, we need the walk-away safe, the passive safe, the low cost, durable, resilient. We need the reactor, we need the machines.
And then add fuel to the list.
Right. But to make the machines, we also have to have the supply chain and the manufacturing capability,
Yes,
right? So,
yes.
I see three major hurdles. Maybe I'll bounce those off of you. So, what are the impediments to the nuclear resurgence, the nuclear renaissance? Well, it's the NRC, which is obvious, and I've written about this a bunch. That agency has slow walked a lot of reactor designs. Now maybe they're getting religion, but NuScale took 6 years and $500 million, and you
Right,
corrected me on Twitter, it was
right.
actually $1 billion. Okay, so 6 years and $1 billion. That's not does a way to commercial success.
I'll give you another problem here. The NRC has never been able to license more than a few reactors a year, and it was approving big reactors. If we switch to SMRs, which has a lot of things to recommend it,
Right.
and we want to make a dent, instead of 1,000 megawatt reactor or 1,200 megawatt reactor, we're going to do 4 SMRs.
Right.
The number of licenses the NRC has to deal with is going to quadruple. So we need a system of...
And the overall capacity may be only equal to one of the old gigawatt scale reactors.
Exactly. So the number of licenses necessary to get 1,200 megawatts online is now 4 instead of 1. If you look at these hundreds of coal sites that people are talking about converting,
right?
These are Truman administration era coal sites, 60 megawatts, 80 megawatts, 300 megawatts.
Right.
We're now not talking about the 92 behemoths we have running now. We're talking about hundreds of reactors.
Right.
The solution is probably not to quadruple the size of the NRC. The solution is to find a more effective, efficient way to mass produce licenses. And I don't mean just, shove them out the door. You still got to be careful with these things, but there's got to be a more efficient way to get these things done.
Well, I that's a really good point, and I hadn't thought about it in those terms. So I'm glad you typified it that way. So I see 3 buckets, right? The NRC, the regulatory scheme, right? How do we get these things approved, right? But then we have to build them, right? So we need that industrial base, and maybe that's not as challenging. Maybe it is, but depending on what the design is. But we have to have fabricators, and we don't have that installed base for that now. We do it for automobiles, right? We do for I would say gas turbines, right? But we don't have it for nuclear reactors and the kit that is going to be needed for those things. And then the other part is the fuel. And I don't even want to handicap which one is most important. I think they're all come together, right? But they all are going to have to be overcome. And as I look at this and try and do it in a very sober way, I think, man, I mean, and the fuel one to me is the newest, I guess, and kind of the one that is the most, as I see it, maybe the most intractable in terms of, because of the lead time to make it happen, right? Because if we're going to be serious about that, we've got to start building these centrifuges. We got to get the mines approved. We have to do all these other things now to set the table for the next 4 or 5 years. Centrist alone has already said 4 years.
It's a problem, but let me tell you 2 things that cut in the opposite direction.
Okay.
Many of the new reactor designs are low pressure reactors. The reactors we have now, they run at 1,200 pounds per square inch, 2,500 pounds per square inch, very thick steel done to exacting standards, carbon steel lined with stainless steel, huge pipes that are set up to carry huge pressures, and safety systems that are geared to, if we get a leak, it's going to be a gusher.
Right.
Low pressure reactors, which may not use water as the working fluid, may use molten salt, may use inert gas, may use something else. Low pressure reactors come in low pressure vessels and low pressure piping, and that's easier to fabricate.
No, that's a good point. So X Energy or the molten salt designs, Oklo, then they'll be easier to fabricate. Don't use necessarily a specialty steel, but that fabrication wouldn't be as big of a problem. So am I right to read then back to you? Then you're saying, okay, well then the 2 big hurdles are the NRC and the fuel.
The fuel, there's a lot of uranium around, but it takes time to get geared up. The Canadians, Cameco, has shut down some mines in Canada that it's now reopening. We do have the ability with enough lead time to produce a lot of uranium, and maybe we should be stockpiling that too, or stockpiling low enriched uranium. The Australians can gear up. Kazakhstan is open for business, although how much of the market you want to give, want to rely on them is an open question. Certainly, the uranium resource is enormous. It's like oil, which is, for years people were predicting we'd run out of it, and it turns out that the ability to find it and extract it has grown faster than demand.
Right.
And we're not alone here with uranium. The supply chain for offshore wind is a total nightmare. And the supply chain for certain ingredients of wind and solar is a nightmare. Let me take a step back from that. If you
Sure.
look at the amount of electricity the United States uses now, and you say, okay, we're going to electrify all of home heating, we're going to electrify all of transportation, diesel and gasoline, we're going to electrify all of industry because those things could be carbon free. Not that they are, they might come from burning natural gas, but they could be carbon free. If we do all those things, and just to make things simple, suppose in the year 2050, we have continuing efficiency improvements and continuing growth, and those balance each other out. So what we're talking about is taking the amount of energy we get now from gas and natural gas and oil and coal, and transferring that over to the electric side. Our electric system has to grow by a factor of 2.5 to 3. And if you take the electric system we've got now, it's 60% carbon emitting. So we've got to throw out 60% of what we've got and increase our total to about 250 or 300% of what we got now.
Right.
That is an incredible infrastructure job. That's just, no matter how you do it, some mixture of reactors, wind, solar, geothermal, hydro, whatever else you can think of that's non-emitting.
Right.
It is just an astoundingly immense thing, and we're going to see supply chain issues in all of that, not to mention supply chain issues in mining for the stuff you need for batteries.
Right.
Yes, it's a challenge for nuclear. It is a challenge for everything.
Well, I like the way you talk about that. I think that that's a good way to see the broader picture. And in fact, I'm writing an article now about the grid and the expansion of the grid and how challenging it's going to be. And I think where I look at the nuclear sector, I think, well, where are those places we could put reactors? As you pointed out earlier, it's at these sites of old coal plants, right? Because they have the energy, they have the grid infrastructure, the transformers already there. They have the rights of way. They have them, those wires and poles in place. So,
and they want a replacement industry.
But so where's the prototype for that, or where's the one-off that is going to hopefully prove the design or prove this concept? It's TerraPower in Kimmerer, Wyoming.
Right.
They just delayed that project by 2 years because
of HALEU.
They can't get the fuel.
Yes, right.
So are there other countries that are looking at fabricating HALEU in the meantime? Because as Centrist Energy's investor report says, okay, well, or their press release from February says it's going to take us 48 months if we get the funding to make this happen. Are other places producing HALEU now?
Russia.
Just the Russians, and that's 10X, which is part of
Rosatom. Yeah, exactly.
So they're the single supplier globally right now for HALEU.
Yes, although that's overstating it because there's not much market for HALEU at the moment. Right. There's a potential market for HALEU.
Got it. Okay.
And for years, there have been people who are saying, if we had enrichments of 19.75%, you could do all sorts of creative, wonderful things with a reactor. And if only we could buy the stuff. And then there are the suppliers who are saying, you may or may not ever want to buy this stuff from us. We're not going to build a plant to make the stuff until you've got a plant to use it. And they're saying, we're not going to build a plant to use it until you can supply it. Right. We've been at a standoff. Again, this is a place where government can get involved, can facilitate, can be the middleman.
Right. So which came first, the reactor or the HALEU, or the chicken or the egg, or we can crucify that concept or that meme. But what about Triso? So one of the first questions I wrote down here, Matt, was okay. Well, so explain the different forms of fuel, because we've talked almost exclusively so far about HALEU,
right? Triso uses HALEU. Triso is, you may have heard the term before, pebble bed.
Right.
Billiard ball bed would have been more accurate, but it doesn't sound as good.
Right.
These are fuel elements that are about the size of a billiard ball. It can vary. And they have little flecks of fuel in them, enriched uranium. You could use plutonium. You could use some other things. Covered, it's like risotto, covered in layer after layer of very tough, very heat-resistant material, eventually in the form of a billiard ball, and you got a giant gumball machine. You never shut the reactor for refueling. You dump new gumballs at the top, you pull them out of the bottom, and you let it run. And you then look at each one you're withdrawing, see if it's soup yet, if it's finished. If it isn't, you dump it back in for another run. And each one of these balls is its own containment. And it allows operation at much, much higher temperatures than a water-based reactor. And the hotter the product, the more efficient it is, the fewer calories it takes to make a kilowatt hour.
Right.
The more you can use it for other purposes. This is what Dow Chemical wants to build near Victoria, Texas.
Right.
Because it will replace natural gas. They've got a natural gas boiler down there that's reaching its retirement age. And decarbonization means electricity, but it can also mean direct use in industry without going through an electric stage. But it needs HALEU.
Right. And so just to back up, so that's the Dow.
That's X Energy here
Dow
in Bethesda,
and X
Maryland.
Energy. And X Energy they use this Triso fuel, which, so that's the Triso is a term for the fabrication, the shape, the form factor of the fuel in the reactor.
Of the uranium. Of the HALEU.
And X Energy is their design is a gas-cooled reactor.
That's correct. And I'll tell you, while we're on the subject, something unusual about this project is the owner of the reactor is not going to be Houston Power and Light or some other utility. It's going to be Dow. Mm-hmm. There is a market emerging for private companies that are not in the electricity business to buy reactors. And it could produce some electricity that went back on the grid, but the universe of people who could buy and operate reactors is probably going to grow.
Well, so that's interesting because I've thought about, to me, I mean, there are a lot of interesting proposals out there. The Dow X Energy deal is one that to me is really intriguing because maybe they don't even sell any power onto the ERCOT grid. Maybe they just use that for process heat and use all the electricity themselves.
They might not, depending on daily circumstances.
Sure. But just to go on with that form factor the discussion. So Oklo needs Centrist on their website. They talk about Oklo, Radiant, USNC, X Energy all need HALEU, but that form factor is different. So for an older style reactor, they will be that fuel will be fabricated for low enriched uranium on existing reactors. That's into the fuel bundles that we see that are familiar, right? That long steel tubes that are clad and then lowered into the reactor vessel.
They're a ceramic fuel form loaded into a special alloy tube that lets the neutrons pass through. And to go back half a step,
sure,
all of this goes through the stage of uranium hexafluoride, which you can enrich to any level you want, and then you ship it to a fabricator. And the fabricator can produce conventional fuel bundles of the kind we use now, which, by the way, is exactly what the GE BWRX reactor or the Westinghouse AP300 or NuScale will use. Or you can fabricate it into Triso or something else.
Right. So the fuel bundle, the form factor for the fuel in the reactor can vary, but whatever that is, we're going to need a varying, a different level of your enriched uranium depending on what the reactor is requiring.
Yeah.
So, I mean, if you were going to look at this, I'm going to put you on the spot here. So, of all these companies we've talked about, who do you? I believe I read something that X Energy was going to be able to get HALEU from the federal government, or there was some Triso that was already being fabricated for X Energy.
There is some that is being fabricated. First out of the box for new reactors, I think is going to be 3 reactors that are the smallest departure from current designs. Those are NuScale, which can run on Westinghouse fuel chopped in half. It's 6 feet high instead of 12 feet high, maybe 7 feet high instead of 14. Don't hold me to it. The BWRX 300, the GE Hitachi entry, and the Westinghouse AP 300. Those are all light water reactors.
Right.
And they all use fuels similar to what we got today. And in fact, not only is the fuel, their fabricators ready to make it, it's also licensed and certified. Next out of the box could be either X Energy or Natrium, the project that Bill Gates and others are backing,
Right.
that you mentioned in Kemmerer, Wyoming, to replace a coal plant. That's a really interesting design, but it also requires HALEU. That's a design that has a higher enrichment, and as a result, the machine can use more things as fuel. It can split more kinds of atoms and get heat value out of them.
Right.
And it will dump its heat into a big tank of molten salt. And the salt, to you and me, it looks like a tank of molten salt. To everybody else, it looks like a battery. It can vary in how hot it is, and you can pull heat off it to make electricity at differing rates depending on what the grid is doing at that moment.
Right.
If it's going to serve California, which now has electricity prices that go down to zero or below because they got so much solar,
Right.
then at noon, you're not going to produce much electricity. You're going to be storing up heat. And then when the sun goes down and all of a sudden you have this enormous demand for electricity, you tap that thermal battery, make a lot of electricity. But again, that needs HALEU.
So if I'm going to read back what you've just said, so your bet is then and it makes sense to me that the NRC, the first deployments will be the reactors that have the traditional designs, the ones that were shrunk, smaller versions of what we've been using, which are the light water designs, right?
Closer to traditional, yeah.
Right.
Yeah.
And NuScale already has that design approval from the NRC, but the BWRX 300, I guess they're actually broken ground in Canada, which could be the first SMR and will likely be the first SMR built in North America. And the AP 300, that there's Westinghouse is still going to have to go through the NRC for that, right?
Yes, but for both of the GE Hitachi entry and the Westinghouse entry, they're reusing components that are already used in other reactors, and those components are already approved. It's a little bit like you've got a Subaru in your garage,
Right.
and you notice that you've got two of them of different sizes, and you notice they have a lot of parts in common.
Right.
Although in the nuclear field, it's not just that they've got parts in common, it's that the parts, there's this supply chain for that part, and that there are whole systems that resemble what's already been approved by the NRC.
Right. So they're more likely to get through that regulatory process faster than X Energy using a gas technology, or the high temperature gas, or Natrium using molten salt. So you've talked about Kazakhstan versus Australia and Canada. Is there prospects? And I didn't see anything in your articles for the ANS about the mining part of this, and maybe I didn't see it. But is there a reasonable to assume we would start mining uranium here in the U.S. so we could be self-sufficient on the fuel cycle?
If the price gets high enough, and if we're really determined to do it.
But again, that would require government to be involved.
Yes, and you'd have to think about where you want to spend your limited resources. If Uncle Sam devoted a certain amount to advanced reactor development, a stockpile of low enriched uranium, etc., how much do you want to prop up domestic producers when Canada and Australia are both lower cost producers and Kazakhstan is really a lower cost producer? Right. You might decide you want to hedge your bets, but it's kind of like oil. We've always bought oil in the cheapest place available. Lately, that's turned out to some extent to be the United States because it's a byproduct of fracking.
Right.
And in fact, some uranium is a byproduct of other kinds of mining. But Yeah, you could do it, but you'd really have to want to.
Yeah. So it might be better in terms of, so thinking about bets, right? If the government is going to have to get involved here in a big way, might be better to be involved in the refining side or the processing side than necessarily in the mining side, because that the Canadians could be a key supplier. The Australians, we're going to be friends with them for a long time.
Yeah,
Kazakhstan, maybe not so much, but that it's the enrichment and that and the fabrication part of the puzzle here that is going to be the key if we're going to have nuclear fuel security. Is that a fair way to think about it?
conversion and enrichment. Yes.
Uh-huh.
Fabrication can also be an issue. You may have seen that Ukraine has signed a deal with Westinghouse for Westinghouse to produce the fuel for the Ukrainian light water reactors that are Russian reactors, the VVER reactors.
Uh-huh.
And those in broad outline are pretty similar to Westinghouse reactors. The fuel is a slightly different shape. When you buy a reactor from somebody, it's kind of like having a car you can only take to the dealer for servicing.
Right.
And that it's unusual for a country to then turn to some other company for fuel supply, but the Ukrainians are doing it for obvious reasons.
Yeah. Got it. Well, so let's jump back, and this is maybe beyond the, well, it is beyond the scope of what you wrote for the American Nuclear Society. And again, my guest is Matt Wald, my friend Matt Wald. He's on Twitter at Matt L. Wald, at Matt L. Wald on Twitter. Is the downstream or the reactor side investable? We've talked about all the risks on the fuel side. In getting providing the juice that the reactors, the machines need to run. But what about the reactor side? I mean, do any of these companies, particularly in restructured markets? That's the question I wanted to ask about.
Yeah.
Can nuclear reactors such as X Energy, we talked about them in Texas, and we have the restructured market of the RTO here.
Wait a minute. Yes, you have the RTO there, but in fact, that's going to be primarily a non-electric reactor.
Yeah. Okay. Fair enough. So I'll make the fair point. Can new reactors?
Yes.
We've seen Vogtle get up to full operating output in Georgia. Can the nuclear reactors, large, small, in between? Can
you build them in a deregulated
Can you
environment?
Will anyone build them in a deregulated market? Can they?
Right.
Can they be profitable in a deregulated market?
Well, the nuclear renaissance of 2008, which didn't actually happen.
Right.
There were multiple proposals to build them in deregulated markets,
including one here in Texas to expand the South Texas project, which went nowhere.
Yes. And I should say deregulated is something of a misnomer. It's restructured more than deregulated.
And restructured is the word Ken Lay used in Texas back when
it's got lots of regulations. It's just not the traditional
yes.
Public Service Commission cost of service, blah,
yes,
blah, blah.
Right, yeah.
So there were proposals to stamp out identical reactors and build 8, 10, or 12 of them and build them in pairs in various places.
Right.
And when natural gas was $16 a million BTU back in 2008, that looked pretty sensible.
Right.
Then came fracking. Gas got down so low that even the gas producers were starving to death. And that doomed that renaissance. You could build in restructured areas if you were confident that people were going to pay something of a premium for two categories of electricity. It turns out that a megawatt hour is not a commodity. It turns out that a megawatt hour can have a different value to the system depending on when and where you produce it.
Right.
And also how you produce it. If it turns out that you put value on it being carbon free, and you put value on it being available in the early evening when there's no sun and maybe no wind, and all the solar is suddenly disappearing, and you need to crank up the microwave and the big screen TV and all that stuff when you drive your electric car back into your driveway and plug it in, then the answer is yes. However, what we've got now is a real cutthroat commodity market where I don't care where it comes from. I don't care what the pollution is. Just give me the cheapest thing you got.
Right.
I'm exaggerating slightly.
No, but only slightly. Yeah.
To build in where I live, which is in PJM. PJM used to stand for Pennsylvania, Jersey, Maryland. It now includes a chunk of Virginia, West Virginia, Ohio, Indiana, the Chicago area, Delaware,
and part of Canada too, isn't it? Or maybe
not yet.
Okay.
In order to build in PJM, which is the nation's largest market,
right,
you need some assurance that you're going to earn a premium. Face it, nothing is going to beat the price of solar in the California desert at noon.
Right.
But the more solar in the California desert at noon is worthless.
Yeah.
It's worse than worthless. It has negative value.
Right. Well, let me follow up on that, because this is something you said. The megawatt hour is not a commodity. So, is electricity a commodity or a service?
Yeah, both. However, so let me get back to my condo building, a stone's throw from Washington, D.C., that's wired into Washington, D.C.
Okay. And what town is that in? You're in Maryland.
It's in the village of Chevy Chase, which is literally on the border.
Right. Okay.
And it's a 16 story.
Your mailing address is Chevy Chase, but across the street is Washington, D.C.
Correct.
Okay.
Right. We got a flat roof. It's not shaded. It's 16 stories high. People say, well, why can't we put solar up there? So let me take you in a little adventure on solar and regulations. I can see from
Wald, we only have an hour here.
No. Right. Okay. I'll be brief. I can see from my window houses that have solar on the roof,
right,
and they get something called net metering,
right,
which means that if they use 800 kilowatt hours a month and they produce 700 kilowatt hours a month, they only pay for 100. They pay for the difference.
Right.
But they only pay by the kilowatt hour. My building is on a commercial rate. We pay for kilowatt hours, but also kilowatts. What is our highest level of demand? Because we impose two different demands on the system. We need energy, but we also need capacity. We need the local electric company to be ready to run our huge air conditioning system all year long, because for a few hours in August, we're going to need it.
Right.
So we get billed that way. We don't get billed just by the kilowatt hour. So if we put solar on our roof, we again get net metering, which is for every kilowatt hour we produce, we get billed for one fewer kilowatt hour. And for every increment that we cut demand, we get billed for less demand. We pay $3.45 per kilowatt of demand. A kilowatt will almost run your hairdryer. It'll almost run your microwave.
Yeah, right.
It turns out that putting solar on our roof will not cut our kilowatt peak demand one bit, because solar peaks at noon. That's the definition of noon. Our peak demand always in the summer, which is what our peak season, comes late in the day when it's hotter. Sometimes it comes after sunset.
Yeah.
So solar makes economic sense for the houses around us, but not for my apartment building.
So is it a commodity or a service?
Or a service.
It depends.
It depends. So the states and the District of Columbia have set quotas, how much solar each electric company has to use. And the electric companies don't actually use the solar. When you make a kilowatt hour on your house roof, on your apartment building roof, you're making a kilowatt hour, but you're also making something called a REC, a renewable energy credit.
Right.
And we can sell those to the local utility. Turns out the price of RECs in Washington, D.C. is astronomical, because good environmental jurisdiction, they've set a very high quota and they're nowhere near meeting it.
Right.
So the price has gone way up. So we can sell our RECs into the District of Columbia. We would lose bragging rights because somebody else gets the right when they buy the REC. If we had confidence that the REC prices were going to stay that high, it might make sense to put a little solar on the roof.
Right.
It won't power much of the building. It's a 16-story building. It's not all that big a roof.
Right.
But we don't have that confidence for a variety of reasons, one of which is the District of Columbia and possibly the state of Maryland are eventually going to back off those goals because we're not going to meet them.
Right.
Which, by the way, is one of the reasons we need nuclear.
Well, let's talk about nuclear. I want to just talk briefly about Canada, and then there's a new IEA report on investment that just came out. Canada, their CANDU reactors, the Canada,
Yes.
the design is really showing its resilience now. They can use natural uranium for their
Yes.
fuel. U-235 that's enriched at less than 1%, 0.7%.
It's not enriched. It's natural.
Yeah, it's not. Okay,
yes.
right. Okay, right. So
it's one part in 141 is U-235. Yes.
So is that it seems like that's just an enormous advantage for that design and over other designs. Is that a fair, Chris Kiefer's a friend of mine. He's been an incredibly effective advocate for Canadian nuclear. And he says, yeah, we just burn dirt. And, that would the CANDU design be a way around having to deal with all these issues we've been talking about around enrichment? Is that a possibility that would be a design that we could adopt instead?
It might. Let me give you just a little history.
Okay.
After World War II, countries decided any self-respecting country was going to have a nuclear program. Canada said, well, the U.S. has got one. We're going to have one too. In the U.S., we said, we're going to have one too. Damn it. And Canada said, we're going to have one too. Sorry. But it required two technologies they didn't have. One of them was a reactor vessel that could withstand high pressures. This enormous pot you put the reactor in, and the other was enrichment. They didn't have either of those things. So they came up with a design that didn't require either one. The CANDU reactor has long tubes, calandria tubes. The fuel is packaged in something vaguely resembling a coffee can. You get a machine that shoves it into the tube. It goes around to all the tubes, keeps shoving in more fuel. At the other end, there's a pool of water, and every time you push one in, something falls off into the pool of water. It's spent fuel. Because it's natural uranium, you can't use ordinary water as the moderator, as the thing that slows down the neutrons to a speed that's going to make another fission more likely to sustain the chain reaction. You have to use something called deuterium, which is the do in CANDU. It's a pun, like a can-do attitude,
right?
But it's Canadian deuterium,
right?
So you got to scavenge that out of the oceans, which you can do. It is a rather energy-intensive project. And I think one of the reasons the Canadians did it is they could provide employment for depressed areas like Nova Scotia, which could burn a lot of coal, which you use to evaporate water and differentially enrich the water with deuterium.
Right.
The Indians have built a few. There have been a few built around the world. It's a perfectly good design. But over the years, the price of enriching uranium has gone down, down, down. The amount of electricity needed to enrich uranium has gone down because the technology has improved. We've gone from gaseous diffusion to centrifuges. Centrifuges have gotten better and better. And we may eventually come up with a laser technology that yet again cuts the footprint, cuts the electricity needed, et cetera.
The Silex technology you mentioned.
Silex would be one possibility, yes.
Right.
So it makes CANDU look a little less important than it used to be. And I got to say, I have great admiration for Ontario Hydro, which operates most of these things. I've only toured one CANDU. It was Point Lepreau in New Brunswick, and it's a very effective machine. I'm not sure that's what the world is going to turn to next.
So let's talk about that just for a minute, and then because we're coming close to an hour, is there a sweet spot now? I mean, there's this, the traditional from the days of Edison and Insull. It's been, we'll build a bigger generator, build a bigger machine because you get better efficiency because you have fewer moving parts. You've concentrated your capital on one machine.
Yeah.
The AP 300 megawatts seems like a pretty good, building block size for deployment in terms of the new reactor designs. But do the SMRs, I'll put it this way, does it make more sense to build SMRs, or should we really be focusing on gigawatt scale reactors?
I think we probably need to do both as fast as possible.
Uh-huh.
But Let me go back to efficiencies of scale.
Right.
One issue is after 3 Mile Island, you need a pretty big crew in the control room to operate a current generation reactor. And each crew operates one reactor. You get to NuScale, which is talking about building clusters of 12 small reactors. You're going to have 3 or 4 people running 12 reactors, not 12 people running one reactor.
Mm-hmm.
You get down to micro reactors, 1.5 megawatts. It's going to run a remote mining site or a remote village, or it's going to be backup power at a military base. It's not clear that you're going to have a dozen people running a 1.5 megawatt reactor. In fact, you may not have an operator at all. It may be a remotely monitored machine. So among the efficiency considerations to be dealt with is how big an on-site crew do you need? X Energy, for example, is talking about actually started building regional service centers. So you don't maintain a full complement of service technicians at each site. You have a regional center from which you can dispatch them as needed.
Uh-huh. And remind me, X Energy was one of the biggest beneficiaries of the DOE grant program. They got something over $1 billion. Was it $1 billion and a half dollars?
I think it's 1.2. They didn't get it. It's promised to them 1.2 billion.
Okay.
So I believe the number.
Right. Because I was looking at the Good Jobs First, their data on, tax credits and such, and X Energy ranks among the highest because of that deal.
They and Natrium were the 2 flagship projects. There's a bunch of reactors at a lower level of technical readiness that received smaller amounts to sort of push them along and see whether they're going to be ready for prime time.
Gotcha. So, well, where do you then come down on this, Matt? I mean, I've told you my Japan kind of made me, I guess, it didn't quell my enthusiasm. It just made me much, I think, more realistic. You've written these 2 articles in American Nuclear Society, and I'll link to them in the show notes. Has it changed your level of excitement, your level of belief in the renaissance in nuclear? Has it changed your outlook? Are you more cautious, more optimistic? Where do you come down these days?
Every form of power generation has complications, has environmental complications, business complications, etc. And I'd rather be in the reactor business than, for example, in the solar business, where we've got places like California demonstrating fratricide, cannibalism, where the worst enemy of a solar panel in California is another solar panel in California, because at peak production hours, your output is useless.
Right.
In addition to which, you've got Uyghur slave labor in Western China producing these things, and they got some nasty chemicals in them. I have nothing against nasty chemicals. Nasty chemicals make the world go round, but you got to be careful, and nothing is simple. Wind has various supply chain problems and intermittency problems. There is no simple solution to our energy problems. What we need is a lot of eggs in a lot of baskets. There are no showstoppers for nuclear. Of all of the advanced reactors out there, I have no doubt some of them are going to fall by the wayside. Not all of them will make it to commercialization,
right?
But some of them will. And you got to spend money to figure this out.
So, is that the thing then? We're going to have to settle on 1 or 2 designs then? I mean, is that going to be the ultimate? Should that be a goal that we simplify and say, okay, we're going to have 2 designs where one's going to be a 300 megawatt, one's going to be a gigawatt, and we'll have, or maybe 3, and we'll have a 5 megawatt, something, that.
Well, the French did that, and it worked out well for them.
Right.
However, if you talk about getting to zero carbon, or at least getting near zero carbon output, you realize you're going to need a lot of different kinds of reactors. You're going to need smaller ones for places with weaker grids. You're going to need high temperature models for non-electric uses. desalination, etc. You're going to need some that incorporate storage.
Right.
So no, I don't think it's going to be one or two or three. I think it's going to be a much wider variety. But if I knew exactly which ones would survive, then I'd know where to put my IRA.
Well, so we're right about an hour here, Matt. I want to honor your time. My guest again is Matt Wald. You can find him on Twitter, Matt L. Wald. I ask my guests a couple of final questions, all of them. So what are you reading? We talked about this before we started recording, but what books are on the top of your list or the ones that you finished recently?
Well, I just read Ministry for the Future by Kim Stanley Robinson. It's science fiction, and it illustrated for me an interesting point, which is opposition to fossil fuels. The outlook on the environment gets muddled up with complaints about the power of corporations, the income disparities in the world, political problems of various kinds. And there are real problems out there, but especially for solar, people think I'm breaking the power of the big corporations. Well, that may or may not be true. I don't think it is true, but it's not a way to make energy decisions. I also I liked much better Termination Shock by Neil Stephenson, also science fiction. And this is not aliens flying around in spaceships. This is near future predictions about technology and society, where a group in Texas decides to take matters into its own hands and start shooting chaff into the stratosphere to reflect more solar energy back out into space,
Right.
to cut peak temperatures, and sets off an international crisis because it alters rainfall patterns in India, etc. That one was really thought-provoking.
Yeah. Yeah, that's interesting to me, the whole geoengineering issue. I've had a couple of people on the podcast to talk about that, and after they've gone, and I've challenged them. I was, well, how's this possibly going to work? And they don't really have very good answers. But that's a whole other discussion that we don't have time for here. So, what gives you hope, Matt? We've talked about a lot of sobering things, but there are a lot of technologies that are being developed that are very hopeful as well. What gives you hope?
I'm not sure. We're still waiting for the magic battery. We've been working on it for 30 years and haven't found
30 years? I thought we were working on it since the days of Volta. That's
maybe more. The federal government's been putting big bucks in it since the 1990s. I do have hope that...
And this doesn't have to be about energy and power, by the way. I mean, as a general question, what gives you hope?
No, there's nothing out there but energy and power. You're confused. There's energy and power and environment are at the heart of a lot of what I worry about. I think we have a lot of inventive engineers out there. We have design tools, computerization, that makes it easier to select new materials, process them, design things, get the pace of technological change going faster. We have the opposite also. We have a paralyzing regulatory system. You're talking about transmission. There's a saying in the transmission business that if you ever go to these hearings where you're listening to people discuss a new power line, that the public interest and the interested public are two completely different things.
Right.
We don't have a regulatory system that's geared to dealing with a climate crisis. And in fact, our regulations get more cumbersome every year. And clearly, lack of regulation has caused lots of problems. But clearly, if you want to get a transformation of our energy system, something's got to give.
Well, I'll agree. But I'll read back then. So what gives you hope is our inventiveness. Yeah. No.
Human inventiveness should not be underrated. You can run short of some materials. You end up substituting other materials. The line used to be build a better mousetrap and the world will beat a path to your door. The mouse is evolving, as it turns out, but the mousetraps are evolving also.
Well, that's a good place to stop. So we'll stop there then. My guest has been Matt Wald, my friend Matt Wald. He's on Twitter at Matt L. Wald. He's written a couple of really good pieces, some of the best that I've seen on the challenges of the nuclear fuel supply issue. And those are available on the American Nuclear Society's website, ans.org. And I'll post them on the show notes. Matt, it's been a pleasure to catch up with you, and great
Robert,
work on those pieces on ANS. I thought they
you.
were just really well done, deeply reported, deeply knowledgeable pieces. So glad that you could come on and discuss it.
Thank you. My pleasure.
And thanks to all of you in podcast land for tuning into this episode of the Power Hungry Podcast. Make sure and give us a good rating on one of those podcast rating things, 10, 12, 45 stars, whatever you can do on that side. If you're not following me on Substack, do that too, robertbryce.substack.com. And until the next time, see ya.